Let me ask you something. When you open an app, stream a video, check a stock price, or receive a medical scan result, do you think you're interacting with words? You're not. You're interacting with numbers. Billions of them. Prices, probabilities, pixels, sensor signals, vectors, matrices, flowing constantly, changing relentlessly. Modern software no longer lives in text and forms alone. It lives in mathematics. And this invisible world of numerical computing is no longer a specialized discipline. It is the silent engine powering nearly everything we use today. Today's decisions aren't made at the end of the week, or even the end of the day. They're made right now. Risk engines recalculate exposure in real time. Recommendation systems adapt continuously. Forecasts refresh again and again as new data arrives. In this world, speed isn't a luxury. It's an expectation. And when systems operate on millions or billions of numerical values, even the smallest inefficiency doesn't stay small. It compounds silently and relentlessly. Python is loved for its elegance, readability, and expressive power. But here's the hard truth. Python was never designed for heavy numerical computation at scale. Each loop iteration passes through an interpreter, triggering dynamic type checks, object handling, and memory indirection. Run that once and it's fine. Run it 1,000,000 times and performance collapses. This gap between expressiveness and execution speed became a critical limitation as data volumes exploded. Before NumPy, numerical computing in Python was fragmented and fragile. Developers relied on deeply nested loops that were slow, hard to test, and nearly impossible to optimize. Matrices were represented as lists of lists. Flexible, yes, but unpredictable and error-prone. Memory usage ballooned, bugs appeared silently, and performance-critical systems often had to be rewritten entirely in lower-level languages. Prototyping and production lived in two separate worlds. NumPy didn't just patch these problems. It redefined Python's future by introducing a fast, memory-efficient, multi-dimensional array as a universal numerical abstraction. NumPy allowed complex mathematical operations to be expressed clearly while executing at near-native speed. For the first time, Python could speak the language of large-scale numerical computing fluently. With NumPy, Python stopped being just a scripting language or glue code. Vectorized operations replaced slow loops. Predictable memory layouts unlocked performance. Suddenly, Python could rival long-established scientific platforms without sacrificing readability or flexibility. This wasn't an incremental improvement. It was a turning point. At the center of NumPy lies the ndarray, a data structure built for numerical clarity and speed. Every element shares the same data type, eliminating ambiguity. Data lives in contiguous memory blocks, improving cache efficiency and predictability. And beneath the surface, highly optimized numerical engines perform the heavy lifting, allowing Python developers to access world-class performance without writing low-level code. Python lists are general-purpose containers designed for flexibility. NumPy arrays are precision instruments built for numerical computation. Lists store references scattered across memory, while arrays store raw values tightly packed and predictable. That design difference isn't theoretical. It determines speed, memory usage, and reliability when systems scale into millions or billions of values. Nearly every serious data science workflow relies on NumPy, whether directly or behind the scenes. Its vectorized computations bypass interpreter overhead. Its deterministic behavior ensures reproducibility. And its arrays serve as the common currency across analytics, machine learning, and AI pipelines, connecting tools, models, and systems into a coherent whole. NumPy's influence extends far beyond its own API. It became the shared computational backbone of the Python data ecosystem. From data analysis to scientific computing to AI frameworks, everything converges on NumPy arrays. This standardization is exactly why Python emerged as the dominant language for data science worldwide. Mature engineering isn't about using one tool everywhere. NumPy excels with homogeneous numerical data, but it isn't ideal for unstructured text, database-centric workflows, or GPU-native workloads. Knowing when not to use NumPy is just as important as knowing when to rely on it. Clarity, not force, defines good system design. Enterprises trust NumPy because it has earned that trust. Its numerical behavior is predictable. Its APIs are stable. Its performance is proven across decades of real-world use. In finance, healthcare, manufacturing, and science, correctness isn't optional, and NumPy delivers it consistently. NumPy is more than a library. It is the numerical foundation that transformed Python into a first-class platform for data analysis, machine learning, and scientific computing. It delivers clarity without sacrificing speed, scalability without sacrificing simplicity, and that is why it remains irreplaceable. Not because it is fashionable, but because it is fundamental. If this story of numbers, performance, and possibility resonated with you, then this is just the beginning. What you've seen here is the why numerical computing matters, why NumPy reshaped Python, and why it became the foundation of modern data analysis. But the real power comes from understanding how these ideas connect, how they influence real systems, and how they shape the tools you use every day. That deeper perspective is exactly what the full article offers. It doesn't rush. It doesn't overwhelm. It walks you through the thinking behind NumPy, its role in the Python ecosystem, its impact on scalability, reliability, and long-term system design, and why it continues to matter as data grows faster and systems become more complex. The link in the description takes you to a thoughtfully curated blog that explores NumPy alongside a wide range of related topics, from data science and analytics to performance engineering and modern Python systems. Whether you're a developer, a data professional, or a decision maker shaping technology choices, it's a place designed to help you see the bigger picture, not just the syntax. So if you want to move beyond surface-level understanding and build intuition that actually lasts, take a moment, click the link, and read the full article. Because in a world driven by numbers, understanding the foundations isn't optional. It's your advantage.